Hello and welcome to this video about math. In this video, we'll see how the complex numbers are constructed from the reals. Many people believe that it is just as simple as adding the imaginary number I. But to do it rigorously and properly, it needs to be constructed using field theory. So the first thing to do is to create the field extension of the reals, called the polynomials of x. These polynomials will have coefficients from the real number system. This field extension will be a ring because it won't contain all of the inverses. And here is a sample of what is contained in this ring. All sorts of polynomials. It includes all of the constants because the variable x need never be used. And since x is in the field, it can be multiplied by itself to produce x raised to the power of any positive integer. The next step is to quotient this ring out by this polynomial. This is how to formally write out this set. And this is what this set contains, all reals plus all reals multiplied by x. Using this polynomial to quotient it out causes the polynomials to never be greater than degree 1. So this is why we're using this polynomial to quotient it out, because we're setting x to be equal to the square root of -1 by using it. See here, the solution to this polynomial is the square root of -1, and it can also be the negative of this square root. So now to look at an example. What would this polynomial be in this set? We can factorise it like this, so as to get the remainder and a product of 1 plus x squared. We know that in this set that this polynomial is 0, which is the behaviour it would have if x was equal to the square root of -1. So this is what it is equal to in this set. If you were to set x equal to the square root of -1 and substitute it into the polynomial at the top, you'd get the same answer, because in algebra you can factorise it and still get the same result. So we'll look at why this ring contains all of the polynomials with real coefficients. We'll start with noticing that x is an element of this ring because we've extended it by x. So then x multiplied by itself, called x squared, is also a member of this ring. And then we could multiply x squared again by x to get x cubed, x fourthed, etc. So x to the power of n is a member of this ring. We can then multiply all of these powers of x by a real number and add them together, and the result will also be a member of this ring, which means that all polynomials with real coefficients are also members of this ring. So this is the field that contains all of the complex numbers constructed from the real numbers. We could have just as easily have used the variable I instead of x, so that now the complex numbers are represented by the proper variable I used by mathematicians. Or we could have used the variable j used by physicists and electrical engineers. So now to prove that this set is a field, we have to prove that it is a ring by proving that it obeys all of the ring axioms, and then the extra field axiom, which says that every element has an inverse, except 0. So both 1 and 0 are obviously in this set. So 0 behaves like 0, and 1 behaves like 1. So both of these two axioms are satisfied. Now we'll prove closure in its two binary operations, which are addition and multiplication. We'll set these two numbers to be equal to any two elements of this set. We'll show that the sum of these two numbers is also in this set, and the coefficients can be gathered together to make a degree 1 polynomial like this. So the sum of these two numbers is also in the set, so closure for addition is satisfied. We'll now prove closure true for multiplication. We'll multiply these two numbers together. Expanding this expression out gives us this expression. We can factorise this term. We can manipulate it to be this, so as to get ready to eliminate the x squared term. This polynomial is equal to 0. And so we can gather this expression together to be a degree 1 polynomial, which is in the set. So closure for multiplication is satisfied. Now to show that negatives exist for each element. This is what the negative is for any particular element in the set. We can quickly show that it is a negative. Gathering these terms together gives us this expression for a degree 1 polynomial, and so it is equal to 0. So this is a negative of this element, so this axiom is satisfied. Now to show associativity is satisfied. We'll arrange the brackets so that the first two numbers get multiplied first. We'll expand out the first two bracketed expressions. Then we'll expand it out fully. Then we'll factorize it like this. Then we'll factorize it again, showing that associativity for multiplication has been satisfied. Now we'll do a similar thing for addition. We'll expand out the first two brackets like this. Then we'll expand it out fully. Then we'll insert brackets back into it. And finally we'll insert brackets again, thus completing the proof of this axiom, and so this set is a ring. Now to prove the final axiom, to prove it is a field, we'll have to show that all non-zero numbers in this set have an inverse. That is, another number in this set that can multiply by it to make the number 1. We'll express it this way. We'll set this number to be the inverse, and solve this equation to find it. We can use the fact that x squared is equal to -1 to speed up this calculation. We can unpack this equation into two equations. This one says that the coefficient of x must be 0. And this one says that the constant part of this polynomial must be 1. We can rearrange the first equation to get c as the subject of this equation. Then we can make this substitution. And then we can simplify it a bit, and we can multiply by the denominator to get rid of all the fractions. Then we can rearrange this equation by factorising the left-hand side. Then we can solve for one of the variables. We can then make this substitution to solve for the other variable that we want. And so we have solved it. We have solved for both variables that we want. So I'll just write out these solutions like this. And we can put them together to find the inverse of this number. Now we have to test to see whether it really is an inverse. We'll do this by multiplying this inverse by the number that it's an inverse of. We can simplify this fraction like this. We can multiply out the numerator. Then we can manipulate it to be this, getting ready to eliminate the x squared term. We can then factorise this part of the equation. We can set this polynomial to be 0, because that is how we define this set. Simplifying this equation gives us this expression, which very obviously simplifies to be 1. So this is the inverse of this number. So an inverse exists for every number in this set. So this set is a field, and so we can perform mathematical operations in it as though it was a field, just like with reals and rationals. So I hope that you have enjoyed this video and felt like you have learnt something from it. Please click like and subscribe if you have. Please leave any new thoughts and ideas in the comments, and thanks for watching.